In Module 4, we go over some computational applications that allow us to pull together the material across our first 3 modules in order to solve some practical problems. The applications we're going to look at are root finding, numerical integration, and optimization. Now, as a prologue to these computational applications, we have this lecture notebook that goes over classes. So what is a class and why study it here? We'll get into this deeper in this video and in this notebook, but at a high level, when we find that we're solving many different instances of a particular class of problems, for example, root finding, numerical integration, or optimization, that involves common types of data and method attributes. For example, a mathematical function, some data to set up the problem, and an algorithm perhaps to follow to manipulate these attributes to obtain some particular quantity of interest. It becomes useful to design a class from which we instantiate an object for each particular problem that holds, in a sense, all of this information inside of it. Now, I know I was just reading all of these words in this paragraph here, and that's a lot of words to digest, but we parse it out carefully below. After you get through the notebook, you should really come back and reread this above paragraph, and I will, of course, fix this typo of numerical integration that I just noticed here. You may find it useful to reference the above paragraph even a few more times throughout the notebooks in this module as we begin to define objects that help us solve various computational applications such as root finding, numerical integration, and optimization. Now, our learning objectives for this prologue lecture on classes is to create a superclass and subclass, understand the difference between data and method attributes in a class, create proper docstrings and new attributes to modify and improve a class. Now, the contents are what are shown here, and I won't read them all through you, but you can click on these to jump to different points in the notebook. So get ready. This is kind of a short but deep dive into object-oriented programming in classes. So let's go ahead and get started. Believe it or not, you are already familiar with objects and classes. You really are. Every data type in Python is actually an object, and an object is just an instantiation of a class. Now, list and numpy arrays are some of the more interesting objects we've encountered so far, and you can even read more of on the array objects by following this link. This means we are actually in a good position to now discuss some of the fundamentals of object-oriented programming, or OOP for short. Now is a particularly good time to do so, since improving your familiarity with OOP can improve your general problem-solving ability and also understanding of how many machine learning libraries are designed, which is where we ultimately conclude this course. Some key points to have in mind as we go through this. What are objects in the relationship to classes? From the Wikipedia article on this, if 2 objects, apple and orange, are instantiated from the class fruit, they are inherently fruits, and it is guaranteed you may handle them in the same way. For example, a programmer can expect the existence of the same attributes such as color or sugar content or is ripe. Now, the values of those might be different, but they have the same types of data, even if the values of the data are different. Abstracting that a bit more, we have that objects combine variables, what we often call data, and functions, what we call methods, into a single entity derived from a class. Classes are really nothing more than a template to create your objects. A useful perspective. Suppose you're approaching programming as if you're an architect. There are, in fact, jobs called software architect. Then you can develop a deeper appreciation for object-oriented programming, OOP, and the need for classes. Suppose you want to design a neural net to perform some complex task like image classification. This neural net may involve many different neuron models that are all interconnected to perform the task. You may then decide it is worth constructing a neuron class, meaning the template for these neurons, from which all the neurons in your neural net are just distinct objects, unique instantiations from this class. Each object will hold certain important variables that are unique to that object. For example, They could contain a string variable stating what type of neuron is modeled, along with the weights and bias for the net input function. And these are all things we will study in the Part A lecture notebook in Module 6, along with certain functional capabilities. This could be, for instance, like a fit function, the fit method, that learns the weight and bias from some training data. Below, we're going to explore some basic concepts you will need for the lectures and assignment in Module 4, including some activities to test your understanding as you work through the material. We now discuss how to actually create your own classes and objects. Now, in general, we will make our classes with an instantiation operation, also called an initialization function, that is run each time an object of that class type is created. Many classes like to create objects with instances customized to a specific initial state. Therefore, a class may define a special method named init with 2 underscores on either side of it. And it's a method, a function, so it has to have the parentheses. And this is going to be like shown below. So I have a silly example here that we'll get to, and you'll see below where I have this initialization function for this object. Now, when a class defines such an init method, class instantiation automatically invokes it for the newly created class instance. This is actually very important with the naming. If you don't name this correctly with the 2 underscores on either side, then it won't run upon instantiation. So you need this proper naming with 2 underscores on either side of that init with the parentheses there, usually with parameters passed to it for the creation. Now, this is not necessary. The init method may have arguments for greater flexibility, but in fact, you don't need it to create a class. But it is rather a typical convention to have it, even if it's just a function that does nothing and just returns. So some useful notes about other conventions. You will see that there's a variable called self used almost everywhere within classes. This is, in fact, is often the first argument of any method defined within the class. This is nothing more than a convention. The name self has absolutely no special meaning to Python, but it allows for more clear readability of code and understanding what in an object is essentially a self-referencing part of the class. I highly recommend you abide by this convention. If you didn't want to use self, you could use a different variable, but that first variable you're going to be passing is a self-referencing variable. And so it just makes sense to call it self. We will initially see that the object is a variable parameter for a class declaration. So what that means, if you see this object right here, if you notice when I create a class, I say this is something to make objects. Now, you don't need this. You could leave this blank. It is useful to write this here, I think, in a parent class, and then put in what you're subclassing when we work with subclasses in below. You don't have to do this object here, but I recommend it. It's just good practice. It's a good convention to have. And then when you do the subclassing, it's a lot more obvious what's going on, I think, in terms of what's a parent and what's a child class, or also called super and subclasses. So that's something else that I talk about right here. Now we're set up to get to our silly example. Below, we create a class called I am what I am that is instantiated with a single input variable that we call x. The idea of this class is to turn a variable x into a more, let's call it, self-aware object that can report its type along with other information related to itself. The variable x becomes a data attribute of an instantiated object and is accessible using the dot convention. And we will see examples of this below. The functions defined within the class are called methods and are also attributes of an instantiated object. They are also accessible using the dot convention. And again, we will see examples of this below. These are called method attributes, which means we have data and method attributes. They're both attributes, but one's a data type and one's a method type of attribute. If the last 2 points seem a bit strange, you may recall that a NumPy array has some data attributes like dot shape. When you instantiate a NumPy array, when you create one, you can do dot shape. There's no parentheses there. It's not a method. It gives you just data, information, characteristics about that object. It tells you what the shape of it is. But there are method attributes such as min and max that you do dot min, dot max, and with just parentheses, that will just produce the min and max value of an array that contains a data type like ints or floats, something that numbers that it can order. So notice that a method attribute is a function, right? This is really important. When you use the word method, you should think of a function in your mind and vice versa. Method and function should be interchangeable when you're working with Python. So we use parentheses when calling a method attribute, but not when we call a data attribute. It is common to refer simply to attributes when discussing both of these, data attributes and methods. But make no mistake, they are both different types of attributes. So with that being said, we are about to see our first example. Before we begin, you should really run this code cell to import NumPy and PyPlot from Matplotlib, because we'll be using these packages in the PyPlot module within this notebook. Now, when we go to create our self-aware object, you'll notice that we use the declaration class. So this is similar in format to how we define a function, where we have def for function or method, but here we have class. And then everything's interpreted through indenting. You have the name of the class, you have the parameter that's object. That's optional, but again, is very useful. I recommend that you do this as a convention, just so that it's clear that this is a parent class for anything that might be subclassed from it. You have to have your colon there, and then within that you would define your methods that contain your various other data attributes. So I'm going to define my initialization method first. So you can see that here with the 2 underscores and then init. So when I create this object, what I'm doing is I'm initializing it. You'll see the self parameter, which is first in all the methods, and I'm going to give it a value x. Any variable, really. It's any variable at all. Anything I create and assign to a variable x, that's what I'm going to assign to self.x. So now everywhere within this class, when you see self.x, what it's doing is it's referring to whatever this value was that created this object. So x is now a data attribute. It belongs to this object as this attribute, and it's accessible in terms of the name of the object .x. So you'll see this below. We'll get into the what I am and these other methods like what created me, but you can see that I have these other methods that I can call. So when I create the object, I can do what am I. It has no parameters. There's always the self parameter is always the first one, and then if I had anything else here, that's what I would have to pass to it. But when I have nothing, I'll just do what am I with parentheses and nothing else. And what it will do is it will print to the screen. It doesn't actually return anything, but it does print to the screen the type of data that was used to create it. And then if I say, well, what created me, then it will actually print the actual data x, self.x, which is assigned the x value that was used to instantiate it. And then I just have this really terrible joke, which is to ask it what is its purpose, and it will just print that is classified. I am a dad, and I do have some terrible dad humor in here. All right, just to show how some things work here, I'm going to create an array A. That is this NumPy array containing 1, 2, 3. I am then going to assign to B the object I am what I am that is created with this array A. So when I run this and I ask B, what am I? Now this is a method attribute, so notice the parentheses there. When I actually run this here, let's just kind of zoom in just to see what happens. When I run this code cell, what am I? It'll say, well, you are, this is what it's basically returning. What am I? It's printing the type, self.x. It's a NumPy nd array. That's exactly what it is. That's the type of that it is, because that's the type of data that A is. It's a NumPy array. It's an nd array. If I ask what created me, it prints the output of what A is. This is the same thing as effectively printing A. If I ask what its purpose is, of course I get the terrible joke printed to screen. And the variable A is now the data attribute x of B, right? B is made one of these objects. B is the self variable now. That's what this was assigned, this object was assigned. So when I do b.x, it's as if I'm asking self.x, because B is the object. So b.x is the array 1, 2, 3, right? Which is different than when you print an array, you won't see that it prints this. It prints the actual things of the array. So you can just get some different outputs depending on if you do b.x or b. What created me. but that is actually what A is. Now, let's look at this. We know that certain data types are mutable. We've seen this with the pass by value, pass by reference. So what do you think happens if we change the array A in some way? What if I make the third component, because remember Python indexing starts at 0, equal to 7. So if I print the array A now, I see 1, 2, 7. So let's look at b.x. It's also the array 1, 2, 7. So changing A has changed B. Now, you can delete A from memory. You'll see this will return an error. If I ask for A now, this will return an error because the name A is not defined. I've deleted it from memory. But let's look at b.x. It's still the array 1, 2, 7. So you have to ask yourself, like, what happened here? So think about it for a second, and then I'll come back to that after the pause in this video. All right, did you figure it out? When we delete A from memory, we're deleting the variable. We're freeing up the memory that was stored in the variable A. But that data that was that NumPy array, it still exists in memory. It hasn't been wiped from the position it holds in memory. It's just allowing for new things to be written there. But we can't access them through A. But it's still there, and b.x is still pointing to the place in memory that holds this array. So that's what's going on effectively here at a high level. Now, one of the things we just observed was you can create an object that's based perhaps on some mutable data types, where certain data attributes for that object depend on mutable data types. And if you change those mutable data types, you might actually change things about the object you created based on those. And you might not want that to happen at all. So we need to address this right away. How do I create, let's say, a more stable object when I'm dealing with mutable data attributes that could be used to create it? So in that case, what you want to do is use the copy function. Assignment statements in Python do not copy objects, right? If I assign array A to be, or excuse me, a variable A to be an array, and then I make B equal to A, all I'm doing is assigning A to B. So if I start changing A, B changes. So this is something you really have to be aware of when you're making objects based on different types of data, especially mutable data types. So what we can do for dealing with this is we can make a copy of the object, right? So now it's kind of like passing the values, copying those things into a new object. So you might go back and review in Module 2 the discussion about mutable versus immutable data types in pass by reference, pass by value. And what we're really trying to do is use a mutable data type, but copy its contents so that if we change the contents of the original variable that was used to create a certain data attribute in a method, it won't change those contents because the original contents were copied over. We weren't just assigning basically pointers to memory where things are. So if you want to do this, then import copy, and we can create a different class. Now notice the name of this, because I'm going to make something that's a little bit more stable. I am what I am no matter what you say is the name of this class. I'm again using that optional object parameter for the class. And now the only difference between this class and the previous one is from the copy module, the copy library you could call it, but it's really more like a module. I'm going to create a deep copy of X. You can do shallow copies as well, but I prefer just a deep copy. So this is going to copy the contents of X into the X data attribute of this object. So I'm going to go ahead and run that, and I'm going to run through these similar types of code. I'm going to create A as this array because I deleted it before, the NumPy array 1, 2, 3. B is now one of these objects, so it's created from the class, the template, I am what I am no matter what you say, and it's instantiated with A. And now, when I change the third component of A to 7, but I look at that data attribute associated with B, b.x, it's still 1, 2, 3. So that's what copy does for us. All right, now for something that may be a bit mind-bending. Let's say that we create a lambda function f that is just the simple polynomial x squared plus 2, so it defines a parabola, a simple quadratic function. Now let's say that I use that as the object, that it's its own variable, it's assigned to f, and I make my self-aware object and I call it c, based on that function f. And I ask, what am I? What is this? Well, it's a function. If I ask, what created me? It'll say a lambda function that's located at some point in memory containing the information for that function. If I actually look at c.x, remember x is the data attribute, notice that this says, well, this is this function within this kind of main namespace that we're working in this notebook. It's a lambda function, and it's something that you can evaluate at x. It's saying exactly what this data attribute is. And now I can do c.x of 2, and that would be evaluating this lambda function at 2, which should be 2 squared plus 2, which should be 4 plus 2, which should be 6. That's exactly what's printed to screen here, is 6. Now here's a very important question. Is x a data or method attribute? So it's a data attribute. It just so happens that a data attribute could be defined by a method. But here it is accessible. We do still access it. We can access it without these parentheses at all. And it's fine. So this is its data attribute. It just so happens that this data attribute is itself a function that can be evaluated at some input. Now, have you ever wondered the difference? What is the difference between similar types of objects? So this particular class can help you determine that, this thing we're creating. Let's create a non-anonymous function, so not a lambda function, that does the same thing as the lambda function above and make it, again, more self-aware with our class. So here I'm going to define the variable test as the function that takes in x and it returns x squared plus 2. I'm going to take d and create an object that's instantiated from the template we have above, this class I am what I am no matter what you say, where it uses test instead of f here, which is the same type of function. It performs the same functionality. But I'm going to create the object d now. Now, if I ask it, what am I? It says, well, it's a function. So is this. But if I ask what created me, it says, well, the function test at this memory location. Now, notice the difference. Here, this was a function lambda here. This is this idea of an anonymous function. And here's the function test. It's given this name. Even though we assign lambda to the variable f, it's treated like this anonymous type of lambda function, where it's more like f is just a pointer to this memory location. This assignment is still just, it's assigning an anonymous function. These lambda functions are considered anonymous functions. It's just now assigned to the variable f, but f is just pointing to this location in memory. Here we actually define a function, a variable named test, and that test is located at this memory. It's a slight difference, but this is not an anonymous function. It's not a lambda function. And again, I can take d.x of 2 and it should still record 6. All right, we are prepared to do our first activity after this short break. I end this first video with a discussion of the instructions of the first activity in this notebook and also its solution. So in this activity, we're dealing with classes of polynomials. This activity is motivated by a few fundamental points. Whenever you are solving problems in computational and data science that require you to repeatedly investigate, explore, or perform computations upon the same object, then you should probably start thinking in terms of classes. This is especially true when you start referring to a thing as an object, since that is a giveaway that you are dealing with a particular instance of a class. There are, of course, exceptions to this, and there's also a general movement and tension between two different programming paradigms. One would be functional programming versus object-oriented programming. But that being said, object-oriented programming provides useful abstractions, and it's really up to you to use your judgment to determine the best balance of complexity required in a code to accomplish the desired task with the overall readability, portability, and usability of the code. Now, polynomials are ubiquitous objects in any computational or data-oriented field. From the Polynomial Wiki page, polynomial functions appear in settings ranging from basic chemistry and physics to economics and social science. They are used in calculus and numerical analysis to approximate other functions. Now, you might object, meaning the object as a verb, to thinking of a polynomial as an object, meaning a noun. So using object in two different ways. I know it's a very bad, punny dad joke. But perhaps your objection is based upon the observation that since a polynomial is a type of function, we could just as easily code up any polynomial we wanted as a user-defined function. You could take a more functional programming perspective on this. You would, of course, be correct that we could do this for any polynomial. Unfortunately, there are an uncountably infinite number of polynomials we may consider, and we may find ourselves having to code up many user-defined polynomials in a single code, which not only becomes repetitive, but is also more likely to introduce errors. Also, we are often interested in many properties, features of a polynomial related to its manipulation through derivatives or integrals, which are themselves polynomials. This is a calculus concept. The sign of the polynomial at a particular point, the direct evaluation of it, gives you whether or not it's positive or negative at points, and qualitative features related to its graph, for instance, plotting. All of these might be things you're interested in, and they represent various data or method attributes we may wish to attach to a particular polynomial object. If we took a functional perspective and just coded up polynomials as a function, or just some function that could be used to evaluate any type of polynomial we want at any point, we would have to create all these other methods around that polynomial function that we would have to then pass the information back and forth through all of these functions, like the state of the system, as opposed to just holding all of it in a single object. It makes it a little easier to use. And this is my opinion. You may disagree. In fact, there's no really right or wrong answer here. You again have to use your judgment. But here, what we're going to consider is how to make our own user-defined polynomial class. It is worth noting that NumPy does have a subpackage on polynomials that has its own polynomial class. But by creating our own, we are able to, 1, decide for ourselves what types of useful data and method attributes are associated with it, and 2, get some useful practice on constructing our own classes for something of clear utility in the computational and data sciences. Now, after reading through the rest of this notebook that involves sub and superclasses, child and parent classes is another way to think of them, I really encourage you to create your own activity involving the subclassing of their own my polynomial from the polynomial class in NumPy that contains some useful plotting features. All right, in the code provided below that starts with user-defined, this user-defined polynomial class, we include some fairly extensive documentation within this class, and I'm doing it with proper documenting standards, the standard way in which you should document things. I don't always go through the effort in this class, but it is good for you to see effectively how you should be documenting classes appropriately using community standards. But sometimes I just want to present results and I'm creating this content, and I take some shortcuts with my documentation. But I am using best documentation practices within my code. And in fact, that's a coding practice, is a documentation practice. And I do want you to see that. Now, the to-dos for you. I want you to add missing code documentation for the plot method in both the class docstring and also within the plot method itself. So if you look below, and you should follow best coding practices here, the way I'm presenting it here. So you'll see with this docstring, what I'm saying, I have a short description of what this class is, this polynomial class. It creates a polynomial from coefficients assumed to be given in increasing order. The attributes of this, I have the COEFFS, the cofs for coefficients, and it's of a type list or NumPy array. That's what it should be. I'm not doing any data type checking here with is_instance or anything. That's something you could add if you want, but in the interest of just simplicity and making these things very straightforward, I'm not, but it's a good idea to have. And then I have this description. So here's what the attributes are. These are just data attributes, generally refer to data attributes in this documentation, and methods will be the functions. But I have these coefficients, which should be a list or NumPy array. I have the fact that the first coefficient is the constant term, and the last coefficient, I'm using negative indexing, is the coefficient of whatever the x to the length of the coefficient's term is. All right, and I should actually say to the length of coefficients minus 1. There we go. I fixed my own documentation. And then for methods, I have evaluate x. Now, notice what I said. I'm missing documentation for the plot method in the class doc string and also within the plot method. So here's the class doc string. I have these similar types of doc strings, like saying what the parameters are in these various methods, and if there's things that are returned as well. I usually describe what is returned by a method. But in this plot method, right, there's one data attribute, coefficients. There's this evaluate function method, and there's also this plot method. I have a doc string for the evaluate method. I am missing a doc string for the plot method. And I am missing any discussion of that method in the class doc string. These are things that need to be done. They need to be added by you. So that's the first thing I'm asking you to do. Add that missing code documentation. You should also add a new method called derivative to the polynomial class that has no parameters at all, which means that it should just call self, right? So if you look at these ones, these methods, I'm evaluating it at an x, or I'm plotting it and I'm specifying various parameters that involve the plotting. But if we come back to a previous example, there's like what am I, or what created me, or my purpose. These have no arguments. When I called them, where's an example where I had this, where I called these. I just called the function with no arguments at all. But I use parentheses, but I don't pass any parameters to it. So that's what I'm saying. The derivative argument has no parameters, but it creates a new data attribute, self.deriv, that is itself a polynomial object instantiated with a new coefficients NumPy array constructed. Now I'm going to give some background and details on how to create the new coefficients array within this method below. This is definitely easier than it may first appear. So here I'm going to read the instructions, and we're going to take a pause. I'm going to let you think about it and try to do it, and then I'll show you the solution after that pause. So the derivative of a polynomial follows from the simple power rule in the linearity of differentiation. It basically comes down to this. If I have a polynomial, p of x, because it's a polynomial, I'll use p for the function, p of x, and I have a sub 0, so that's the constant term, a sub 1 times x, so x raised to the first power, a sub 2 times x squared is added to that. That's, x to the second power and the second a coefficient. And I just keep adding these up. I assume I have an nth order polynomial, then I'm going to have n plus 1 numbers defining the coefficients of this. You can think of this as x to the 0. This is times x to the 0, which is 1. This is times x to the first, times x to the second, and so on. So if I have a first order polynomial, I have just a0 plus a1x. Then I have two numbers, a0 and a1, that I need to define in order to define the line described by this linear function. If I have a quadratic function, there's three numbers that you see, a0, a1, a2. So nth order polynomial has n plus 1 real numbers defining it. Now the derivative of p of x, denoted by p prime, so we've seen this notation in module 3, the Part C lecture notebook of that, it's given by itself a polynomial. And you don't need to know why it is what it is, I'm just giving this to you. But p prime of x is given by a sub 1 plus 2a2x plus, and so on and so forth, n a sub n times x to the n minus 1. So each of the coefficients from before are just except for a0. Well, you can think of this as well, a0. They are just given by themselves times what the power of x was in the original polynomial, and then you just lower the power of that monomial term by 1. So a0 times x to the 0, that 0 from the x gets multiplied a0, just goes away. So it's not even there. a1 is now multiplied by 1, the x to the 1 term. So it's a1 times x to the 0. Then that 2 from x squared, 2 gets multiplied to a2, and then x gets raised to just the 1 power. I just keep lowering the power by 1. And then you can see the last one, I have that n from x to the n gets multiplied to a to the n, and it's x to the n minus 1. So there's just a pattern here that we need to follow. The key observation is that for 0 up to n minus 1, so if we let k be an index that ranges from 0 to n minus 1, because we have an n minus 1 order polynomial here, and this is going to define n terms right here. The coefficient of that kth order term in that derivative p prime is simply given by k plus 1 times a sub k plus 1. That's it. Those define the new coefficients, which means we can construct those new coefficients in the derivative method as follows. So when we create our derivative method, you should have something that creates a new coefficients. I would start by creating a NumPy array of zeros. And I'm taking the length of my original coefficients. I'm subtracting 1 because if there were n plus 1 before, now I need n. So I need to subtract 1. If p is order n, p prime is of order n minus 1. So there's 1 less coefficient. And so then for each k in the length of this new coefficients, the number there is, I just need to make the kth one equal to k plus 1 times the previous k plus 1 coefficient. And I'm just using some tech notation kind of here with the subscript and the curly brackets for putting a subscript there. You could just copy and paste this right into the code, but you need that just to get the coefficients. Now, what else should you do? You should, of course, add documentation related to this new derivative in the class docstring and also within the method itself. Now, the instructor, me, provided code cells that follow the class that should run free of error. These are marked with a comment, instructor created code cell, at the top of each such code cell. So if you did things right, that should run just fine. You should create a 4th order polynomial. I didn't do this for you. You need to do it. Compute the first 3 derivatives of this polynomial and create a single plot that contains all 4 functions, the 4th order polynomial and its 1st, 2nd, and 3rd derivatives. So those are your instructions. Try to read through them again. Pause this video. Really try this for yourself. It might take a little bit of time to do, but when you're ready, continue on with the video after the short break and I'll show you the solution. So now we go over the solution to this first activity. All that you need to do is create this one method within this polynomial in order to accomplish the second part of your to-dos, to add a new method. No, I'm not going to add the missing code documentation. I really want you to think about how to do that properly. So you need to add that missing code documentation for the plot method in both the class docstring and also within the plot method itself. So this is the class docstring, right? Because here's the class, here's the docstring associated with that class. You need to add the documentation for it for both the plot method and the derivative method. And these are missing docstrings themselves. You need to put that in. I'm not going to show you how to do that. I want you to really go through the process of properly documenting the code in the style I've shown in this, I've templated for you effectively in this class. But this is it for the derivatives, the derivative method. I create this new coefficients array, and then I loop through and I just use the formula to compute them. It's very simple. I just copy and pasted what I produced above in the code. And then what I do is I create a new data attribute, self.deriv. This is what I asked to do here. Create a new data attribute, self.deriv, that is itself a polynomial object. So a data attribute can also be an object, a class. And I'm calling the same class that is containing this. So it's going to create a polynomial class from new coefficients, and then that derivative data attribute inherits all of the things from that polynomial object, from that polynomial class. It itself, I can take more and more derivatives of it. And you'll see how I do this a bit below, and it's up to you to do this for yourself. But let's go ahead and just run this. So that was it for the code. For the coding part, you just had to add, looks like 1, 2, 3, 4, 5 lines of code. So I believe I ran it. Let me just check. Yes, it ran. And now look what happens if I say help to the polynomial. It gives me information about the polynomial, the class. It plots the docstring associated with it. It says what the attributes are. And then it also gives me the information, these docstrings involved with these various methods. But notice it doesn't have any method or any docstring associated with plot or derivatives. That stuff is missing. So there's derivative and there's plot. And it just is doing it alphabetically, apparently. There's derivative is appearing before. So A, B, C, D, E. Yeah, so it's just alphabetical. That's interesting. I didn't realize it was going to do that. I'm just looking at it now. But now I'm creating a polynomial. So here's an instructor created code cell. P is a polynomial. It creates this second order polynomial. 0 plus x plus 2x squared, right? Because that's exactly what I'm doing. I'm presenting the coefficients in increasing order for the monomial associated with it. So 0 plus 1 times x plus 2 times x squared. So P is now a polynomial. Now I have attached to this polynomial this plot function. Notice what I do for plot. All I have to do is pass it xmin and xmax. I have to say what those values are, and I'll quickly generate a plot with 100 points. It's going to make this array of x values for plotting that's going from xmin to xmax using n points. It's doing a linspace. I'm going to create a figure with that given fig number. I'm going to make it a blue plot and with a dotted line style. These are parameters you could change, but I just designed some default values so that when you create the function, this polynomial, it has the ability to plot itself. So this object, this polynomial, I can now quickly plot the polynomial between -2 and 4 because I'm positionally passing it the xmin and xmax. This is just that first argument, but it's not actually passed to the plot when you call it. It's just that self-referencing object. That has to be the first argument, but it's not actually something that you pass when you call the method. So this is putting -2 and 4 for xmin and xmax here. Let's go ahead and plot this polynomial. So there you go. There's a plot of your polynomial, and it has that blue dotted line. Now here's where I'm going to create another object. I'm going to call that derivative function. And excuse me, I'm not creating another object. I'm creating that data attribute now. If I actually looked, so I'm just going to create a code cell here. In fact, no, I'm going to delete this. I'm going to bring this down. I'm going to put a scratch code cell in here. So insert a scratch code cell. I'm also going to reformat this so that it's side by side. So I want to change the page layout to 2 columns. There we go. Now, p.deriv, right? That's supposed to be, when you look at this, that derivative attribute. If I call this, look at this, I'm going to get an attribute error. It says the polynomial object has no attribute deriv. And you can say, well, it's right there. It's right here. It doesn't get created until you call this method. So now let's go ahead and create this derivative, p.derivative. Now when I call this, p.deriv is a polynomial object. So that data attribute is now a polynomial object, but it doesn't get created until I actually run that method. That's just the way that class is defined. Now I can plot the original function to -2 to 4, and because I set this figure number as a default to be 0, everything will be plotted on the same figure. I can also plot the derivative, because the derivative is a polynomial object. It has the plot function attached to it, and I can also plot a -2 to 4, but now I can pass it different color and line styles so that I know what's plotted in red with a dashed dotted curve will now actually be the derivative plot. So the original plot of the function will be in blue, and in red will be the derivative. And there you go. In blue, there's the original polynomial, the quadratic, and in red is the derivative. And now I can actually compute the derivative of the derivative. So this is the second order derivative. And now the second order derivative is just a constant, actually, because the derivative of a linear function is just going to be, in this case, in 1D, it will be the slope of the line. And in this case, it's 4. You don't have to, it doesn't matter why that is. But now I'm going to plot my original function. I'm going to, in red, plot the derivative. And then the deriv attribute now has a deriv attribute, which is the derivative of the derivative. And it then is a polynomial object, so I can plot it. And I'm going to plot it in black as a solid line. And there you go. Now all 3 of these are plotted together. And if you wanted, you could imagine that you attach like labels to these plots. You could try to enhance this so that you could make legends out of this. You can try to get fancier and fancier with this, but I'm just trying to illustrate some basic things. So now you should work in this code cell. So what I've done to this point is I've shown you how to do the coding part. I haven't done the documentation for you. You need to do that, to add in missing code documentation to the plot method in the class docstring and within the plot method itself. Do the same thing for the derivative method. You need to add a docstring for it and also within the method itself, within the class docstring in the method. These instructor provided code cells run without error, and hopefully you understand what they're doing, why they're creating what they're creating. You need to create your own 4th order polynomial and compute the first 3 derivatives. It's very similar to what's going on here, but I want to see you do that for yourself. I created a polynomial and I showed you how to take the first derivative. I showed you how to plot it on the same plot as the original function. I showed you how to take the second derivative. I showed you how to plot the function, the first and the second derivative all on the same plot. I want you to create a 4th order polynomial. I want you to take the first 3 derivatives and I want you to plot them all on the same plot with different colors and line styles. That's what I would like to see.
That's all you need to do to finish this activity. Good luck.